Okay, hello everybody. I'm making a second video today just to kind of catch us up with what we did last week. So I wanted to talk a little bit about the automatic pitch tracking portion of the DSP homework because a number of people struggle with that. And in fact, there's only one person who really got it right the way I imagined it would be. And so I'm going to embarrass that person in this video. That person is Benjamin. And I want to walk through his answer to the question. So if you remember, basically we had two sort of mystery waves, and we were trying to figure out what the fundamental frequency of these two waves is or would be based on an analysis that only looked at three potential fundamental frequencies of 8 hertz, 10 hertz, or 12.5 hertz. And to figure this out, I wanted you to walk through the process I talked about in the lecture on pitch tracking and determine the value of R for each of these three possible fundamental frequency values. And then the tricky part that kind of messed a lot of people up was the window part. So you have to look at a window that starts at the first sample of each wave and is 3 times as long as the longest period you are checking in your pitch analysis. And I wanted you to take that approach because that's the approach that Prot takes when it does pitch tracking itself. And the criterion, again, is that that window length has to be 3 times as long as the longest period you are checking in your pitch analysis. So the first thing you have to do for this problem is to look at the various periods you're checking in your pitch analysis, which you can only figure out by first looking at the fundamental frequencies you're checking. So we've got 3 options here: 8 hertz, 10 hertz, or 12.5 hertz. So just as a bit of a reminder, frequency and period have an inverse relationship in acoustics, and I think I've got that listed on here somewhere. Maybe I should. But if the frequency of a wave is 8 hertz, its period is going to be 1/8 of a second. I don't seem to have it in this particular lecture. It's probably on the previous one. But yeah, no, I should have it. It's been a while since I looked at this. I apologize. But that's basically the gist of it, is that frequency equals 1 over the period. So if the frequency is 8 hertz, it's 1 over 8. 1 over 8, or 1/8 of a second, is the period. If it's 12.5, it's 1 over 12.5. It would be the period. And 1 over 8 is going to be longer than 1 over 12.5. 1 over 8 is 1/8 of a second. That's slightly longer than 1/10 or 1/12.5, whatever that is. Anyways, our longest period is going to be 1 over 8 seconds, 1/8 of a second. And what I need to get is a window that's 3 times that length. So 3 times the longest period, which is 1/8, would be 3/8 of a second. So that's 3/8 of a second, or if you do the conversion, it's 375 milliseconds. And like I said, Benjamin got that right. And he also organized his response in a very nice way, which I think makes it clear what he was doing. So I'm going to walk through that a little bit. So this is the original waveform for pitch track number 1. And it's in digital format. It's been digitized, and it's 2 seconds long. So basically we have these individual time points, and then they each correspond to a different amplitude value as we go through the wave here. It's sampled at 1,000 hertz frequency, so there's 1,000 samples per second. There's one every millisecond, and then that each millisecond corresponds to a different amplitude value. So just to go back to the lecture, which I was messing with before, we're looking at a waveform that looks kind of like this one down here on the, well, I mean, actually this is the original, and then I'm chunking out this first window here, starting at time 0, and then going to some indefinite point on the right side, although we figured out in this case it's going to be 375 milliseconds on that right side. That's the first window I'm looking at. And if we go through Benjamin's response, hopefully you can see this. Maybe I'll make it a little bit bigger to help you out. So this is the original, and then he has what he calls chunk 1 here, or window 1, I guess you could say. So he's got time for T for time, and then A for amplitude. So this is that original window, this little snippet over here on the left. Oops, didn't mean to do that. We'll go back to that. And it goes for 375 milliseconds. So all the way up here to 375. Technically speaking, he only needed 375 samples, and he could have stopped at 374, but 0.374, but don't worry too much about that. But that first window is right here. And then kind of the crucial point is all the other windows are going to be the exact same length, right? So he's looking at chunk 2 here, which by the way starts at 0.125 seconds, or 1/8 of a second. And then he's making that as long as that initial window was. So that extends out to 0.5 seconds, or half of a second. So to give you the visual analog, so this is his chunk 1 over here, and he splits that off over here to the left. And this is chunk 2. He's grabbing it from the same original waveform and then splitting it off here over to the right. But that difference, the only difference is when chunk 2 starts. So they're both the same length, the exact same length of 375 milliseconds, but chunk 2 starts 1/8 of a second later in the waveform. So it's down here. That's where it begins, rather than at time 0. And having done that, he's now got this chunk, and he's got this chunk, and he wants to see how well they match. But he's going to have to do that in numeric formats, right? So these are the amplitude values for chunk 1. They go all the way down. And then these are the amplitude values for chunk 2. And what he does there is walk through that process for calculating R that I told you about in the lecture before. So basically, these are the products. So he's multiplying this value. Maybe if I double click on this. Yeah, so he's multiplying this value by this value. In the first case, is 0 for both, so it's boring. It just turns out to be 0. In this case, it becomes something more interesting. 0.565 times 0.565 equals 0.319. And actually, if you do this, I might as well point this out. This kind of starts to give you a clue. Like every single one of these amplitude values matches. So what's up with that? It seems like the whole period waveform is repeating just 1/8 of a second later. And in fact, it is, because it'll turn out that the actual period of this creature is 1/8 of a second, or 0.125 seconds. And you can see that just because all the numbers match up, which would mean that the waveform would look exactly the same. It would start at the exact same spot, it'd go through all the same bumps and valleys, and then it would end at the same spot if we looked at it graphically. We can't do that, though, because we're pretending to be a computer and we're just looking at numbers, but that's, you know, if you've gone through this problem and you saw that pattern, that's a big clue that you're sort of on the right track, that that's the actual period of this waveform. Then nicely, he kind of organizes it where he copies chunk 1 over here again, and then also matches it up with chunk 3. So the only difference between chunk 2 and chunk 3 is when they begin. So chunk 3 is the one he's using for the 10 hertz frequency possibility, because it starts at 1/10 of a second, or 0.100 seconds. The first frequency he checked was 8 hertz, so that would begin at 1/8 of a second, 0.125. The second is 10 hertz, that begins at 1/10 of a second, or 0.1. And otherwise, these are the exact same length, which is kind of the crucial thing that a lot of people didn't pick up on. So this one goes out another 375 milliseconds to 0.475. And you can see, because they take up the same number of rows here in the Excel spreadsheet, they're the exact same length, right? So it goes through the same process of that in calculating R. He just multiplies the amplitude values by each other, gets a variety of products, or a whole series of products. And then at the bottom, I forgot to mention this before, but he sums up all of those products down here. So he's basically just saying, take total of all these guys, and that will be my R value. His R value here is 37 something. His R value for 8 hertz is 121. He'll do the exact same thing for the 12.5 hertz chunk, which begins at 0.08 seconds, or 1/12 and a fifth, 12th and a half seconds. I'm not going to say that again. Don't worry too much. But yeah, so that's where that chunk begins, and otherwise it's the same length, right? It's 3/8 of a second long. So that winds up ending at 0.455 seconds. He calculates R the same way by multiplying the amplitude values and getting the product. And then at the bottom of the whole thing, he gets a sum of 34.8. So down here, what he can do is just compare these R values and say, well, hey, lo and behold, this one's the winner because that's the biggest R value, which is the correct answer, right? So, I mean, we could have figured that out, again, by looking at how these amplitude values just repeat over time, if you kind of catch them at the right point in the cycle. But you can also just do it the kind of mindless way and say, well, this is the biggest R value, so that it has to be the best frequency option, which it is. And he wrote that up in succinct fashion here by saying the R value of chunk 1 and chunk 2 had the highest value, and the offset between the two chunks is that's all you needed to do for this one. And he did pitch track number 2 in basically the same fashion. This one, though, the R value that was highest turned out to be the one for 12.5 hertz. So if you go down here, it's about 151. The others are very small, but so that winds up being the correct answer, 12.5 hertz. I'm going to embarrass somebody else here. I'm going to embarrass Sean, hopefully not too much, because Sean basically did this the right way too, but he made a common mistake, which a lot of people did with this exercise, unfortunately, which is to not make those window lengths the same length. So he multiplied the window length by at 3 times the period he was checking for that frequency. So for 8 hertz, it's a 1/8 period, right? So he multiplied that out by 3, and then he got a window length of 375 milliseconds. So he's all the way down here at 375. I don't know if you can see that or not, but maybe I'll make this bigger. Yeah, so that was right for that one. But for the 10 hertz frequency, he was just multiplying 3 times 1/10. So the period of a 10 hertz frequency sound is going to be 1/10 of a second. And he was checking a window length of 3/10 of a second for that reason. But what he needed to do was actually check it all the way out to 375 milliseconds to give it like a level playing field across all the three different frequencies. So for that reason, he wound up getting, where are his R values here? So here are his R values. And for this reason, in this particular case, he gets slightly bigger R values for 10 hertz and 12.5 hertz. He still gets the same answer. So in the sort of the correct way of doing it, there were about 37 and 34 for 10 hertz and 12.5 hertz. Here he gets 96 and 77. So they're much bigger than they were before, but they're still not as big as the 8 hertz frequency option. So he got the right answer in that sense. Over here, he just kind of didn't quite do it exactly the right way, and that winds up costing him for the second mystery wave, where he gets a bigger R value for the 8 hertz and the 10 hertz than he does for the 12.5 hertz. And that's kind of the moral of the story. Like I said, you want to have the same window length for all the different frequencies so that you can kind of put them all on a level playing field, because at the end of the day, you're trying to compare R values with each other, and you want to pick the R value which is biggest. But if you have a longer window for 8 hertz, you're going to have more numbers you can sum together for 8 hertz, and you have a bigger likelihood of getting just a bigger number at the end of that, because I got 375 samples here compared to just 240 samples for my 12.5 hertz token or frequency option. And then lo and behold, I wind up getting a bigger R value here, even when I shouldn't have. Yeah, I mean, there is probably something else going on with this one as well, because which I haven't checked exactly, because this one should actually be quite a small value in this particular case. If he's calculating it the right way, it should be like 2 or -0, but negative 0.4. But you know, he's basically doing it the right way. Just the one problem here is the window length problem, and I don't know of a better way to make that explanation clear without telling you exactly what it is, but now I'm telling you exactly what it is, since you've given it a shot. But that is sort of one crucial problem that a lot of people had with the homework. So I don't want to just pick out Sean with respect to this. He's just sort of representative of a general problem. Otherwise, like I said, Sean did this the right way, effectively. And I like the little write-ups here as well that both Sean and Benjamin gave to just sort of clarify the overall point of what we're doing with this exercise. So hopefully that helps this one make more sense. If you still have questions about it, you can always write me an email or ask whenever during office hours. That's all I'm going to say about it for now. The downsampling didn't cause as many problems, but it's also not as complicated. But just keep pitch tracking in mind, again, because we're using it a lot, right, for these Toby transcriptions. We look at pitch tracking results all the time when we're looking at intonation and other things like tones and whatnot in phonetics. So it's important, and the computer helps us a lot, but the computer makes mistakes in certain contexts, right? So we have to know what the computer is doing to know how to interpret those mistakes that it's showing us. Again, as usual, it's helpful to use the force and just like be a human about this and have an intuitive sense about what you're looking at. The computer is a tool that we're using to help us along the way. But to be a computer, you have to do stuff like stare at all these numbers, and we don't want to do that. But still, you're more important than the computer at this point. So just keep that in mind. and hopefully trust your instincts to the maximum amount possible. And then we'll sort out these technical details as we go through the whole process. All right, I've talked enough for now, at least especially for one day, but I'll be back again probably on Friday to talk some more. So I'll see you then.